My initial idea for this talk was a little different, but I adapted it to be a little different from Helen's talk, in the sense that we saw all the background for AGN feedback, and thank you for that, so I don't have to do that. But for this presentation, I wanted to focus about work that has been done in the narrow-line region of nearby Seyfert Galaxies, and most of this work that is going to be presented here is covered in this review by Pepe and Martin 2022, and actually it's where this background image came from. So I really I suggest that you go and check, because it's a really interesting text. But this talk, the way it's organized, I will talk about the works that have been done in this AGN-host interaction in the nearby universe. But at the end, I'll also include some of my contribution and some new results and very interesting results. So you can think of this as a sort of review of what we know and what kind of science can be done with access in the future. So I'll start talking about why we choose obscured AGNs or compton-thick AGNs. Why are they so important to study the extended X-ray emission and this host AGN interaction in the nearby universe? So there are two main reasons. The first reason is because of the unified model. As we can see here, when we look at this AGN, we are seeing them through the torus, and this leaves you with the outflow bicones lying close to the plane of the sky, which maximizes that the projected extent. But also that torus is also obscuring, it's cutting down the intensity of the central unresolved point source. So that allows us to look at that faint extended emission that can be seen extending along the winds of the Chandra PSF. So here, just three of the galaxies that I will be showing lots of results on these galaxies today: 4151, Markarian 573, and 3393. These galaxies, 4151, the work with Chandra was done by Young et al., and then Markarian 573 was done by Alessandro Paggi, and 3393 was done by Peter Maxine and also by Pepe. So this I like. I know it's a lot of information, but this is just for the effect of it. So this is a table that is extracted as exactly as it is from this review paper, and it shows the 27 nearby Seyferts at the time of writing, where we studied soft X-ray extent in high resolution Chandra ACES X and ACES S. And I think I hope that you can see this, but the structures they're seeing in these galaxies, they range over a factor of 100 in their physical sizes. So you're going to see extended X-ray structures from 30 parsecs extending all the way to 3 kiloparsecs. And usually when you are imaging these structures, you require a good signal to noise, and that usually translates to about 100 kiloseconds with Chandra ACES. And here we can see, I think 25 AGNs that at that time have been detected with soft X-ray emission and were mapped with Chandra. So one thing that is really interesting about this extended X-ray emission is that the extended soft X-ray emission can be traced farther out, and I'm going to show you in a couple of slides from now how you do it. But the soft structures, the soft emission structure that is reviewed by Chandra, shows a very good overall alignment with the axis of the extended narrow line region, and also with the radio structures. And again, we are seeing that those galaxies again. Here we have images of these galaxies in 3 different bands: HST, Chandra, and radio VLA. And we can see that, especially for the optical and X-ray images, that you have a very overwhelming coincidence, like spatial coincidence of these emissions. So one of the fun science, let's say, that it can be done with X's, and it has been done for these targets, is use the lines that can be detected and their ratio to use as diagnostic of the emission processes. So basically, here we are seeing a close-up view of the neon emission line image from NGC 4151. And this work, again, was done by Yang et al. 2011. But if I remember correctly, there are lots of papers on this galaxy. And this is actually one of the interesting things about working with these targets and working with the AGN-ISM interaction in this target, is you can see the evolution of your knowledge, let's say, on each target with each passing time. So this was done in 2011, and at the end here, I'm going to show you some work that was done in 2014 also on this galaxy. So one thing that you can see here is, again, you're looking at the neon emission line image, and here you are just looking at the ratios of the neon to the 07 emission in the narrow line region of this AGN. And looking at this one here, we can see that there is a factor of about 2 in change of the ratio across this narrow line region map. And this clearly shows that the conditions across this soft X-ray structure are not uniform, and that you can have multiple emission mechanisms that can be contributing to the emission detected in each of these locations. So then, if you try to fit this entire emission with just a single component, if you try to model this entire structure here as a single component, you lose lots of information. So that's one of the topics that Access is going to contribute the most, is to disentangle these emission lines and to break this degeneracy between these emission mechanisms. So what is being done related to photoionized and shocked emission in nearby Seyferts has shown that the thermal emission that they detect seems to be dominated in regions of strong interaction of the radio jet. So if you remember from my previous slide, this galaxy has a radio jet also aligned with the axis of the bicone here. So these emission features, these thermal emission features tend to dominate in regions of strong interaction of the nuclear radio jet with the ISM. And I'll go back to that in a little bit, but the way you can get information about what's going on in these with these processes is that you can get the X-ray temperature of this gas from modeling, and they'll give you a good estimate of the speed of the shocks that might be happening in that region. So one of the, to me, I came from an optical background. So when I started doing X-rays, one of the most interesting things to me is the fact that Chandra has been reviewed extended hard X-ray emission as well. And when I talk about hard X-ray emission in the narrow-line region of these AGNs, I talk about hard continuum, which usually we talk between 3 and 6 kV, and also extended emission in the 6.4 kV iron K alpha line. So usually, or from the unified model, we would expect that the hard continuum, as it arises from the reflection of the hard photons from the AGN on the clouds of the torus, we would expect that these emission would be seen as point-like. But we know that it's not like this, as I said. So here we have a deep Chandra image of ESO 428, which was done by Pepe in 2017. And this was the first time that it was showed extended hard continuum, which is this image here, 3 to 6 kV, and also extended iron K alpha emission on a comparable kiloparsec scale size. And this is, I'm comparable because it's comparable to the soft X-ray extent in this galaxy. And after this galaxy, many other galaxies were found to have this extended hard emission, both in the hard continuum and also the iron K alpha band. So you have, for instance, NGC 7212 by Jones et al. 2020. There's also a very good paper by Ma et al. 2021, in which they analyzed the occurrence of extended X-ray emission or extended hard X-ray emission in the narrow-line region of Seyfert in the nearby universe. So that's also a very good paper to take a look at. So one of the interesting things is when this extended hard emission was discovered, the idea is that you have photons that are interacting with molecular clouds that are just lying in the plane of the galaxy. So this energy dependence, the energy dependence of this emission, as I'll show, suggests that in the case of the hard band X-ray, these clouds, the molecular clouds that are responsible for scattering these hard AGN photons, they are more concentrated, is smaller radii. So I don't know if I'm going to have time to discuss this, but just in a nutshell, before I move on to my results, one of the things that have been also found by Chandra in the narrow-line region of nearby, in a few nearby Seyfert galaxies, is extended iron 25 emission. And this is NGC 6240 and was studied by Yang et al. In 2014. And here in this paper, they relate the extended iron 25 emission that they discovered to shocks due to the radio jet in that narrow-line region. So this was a very quick and brief review, and that was was just a background to come to this, which are my results. So this is my small contribution to the study of AGN-host interaction in the nearby universe. And this is NGC 5728. And this is a very interesting target because it is close by. It's about 40 megaparsecs from us. And because it's relatively close by and the nucleus is obscured, as we saw, it makes a great target for studying strong AGN-host interaction and AGN feedback. So NGC 5728 has been a subject of higher resolution studies for a couple of decades now. So both of these images are from a 1993 paper by Wilson et al. Using HST planetary camera data. And more recently, you have this image from Duhamel 2018. And here the image is O3 from Muse, and then you have the radial contours in green, and the X-ray contours in blue. And what we can see here is, as we saw for the other galaxies that I showed before, the radial jet here is directly in the plane of the galaxy. And based on the optical analysis of this galaxy, it's based on the multi-wavelength analysis of this galaxy, it's supposed to be, this radial jet is supposed to be directed with some of these dense clouds at a few hundred parsecs from the nucleus. So, when you analyze an AGN, you first start by literally just looking at it. What do you see? So this is a 260 kilosecond observation for this AGN. This is actually, this is merged. These are merged observations. I merged 11 observations to get the total 206 kiloseconds. And here it's why you need good resolution, because when you go down to 1/8 pixel, which is the case of all of these images, then you start seeing all kinds of really, really neat features that go even beyond that gross association that we saw before between the narrow line emission and the X-ray emission. So how can we study the narrow line region of these galaxies? And this is what I mentioned before about how you can measure or quantify the extent of these X-ray emission. So basically what you do is you compare the surface brightness of this emission in certain regions to that of the model PSF or the expected emission from a point source. So here in black, we are seeing the surface brightness of the galaxy, and it's a little complicated the way that this is shown here because this talk is condensed from a much longer talk. So I'll try to make sure that you have all the background. We divided this galaxy into cone and bicone, cone and cross cone regions. Basically, cone is the direction of the ionization by cone, and the cross cone region is the direction perpendicular to that direction. And in here, we analyze these extended X-ray emission in different energy bands, as you can see, and we also analyzed it in the two different directions. So one of the things that I didn't have time to mention, and it's extremely interesting as well, is Chandra has also uncovered extended X-ray emission in this cross-cone direction here, which is the perpendicular direction to the ionization cone. And if you think about it, it's extremely surprising because based on the unified model, you expect to have, you don't expect to see any emission coming out from there. So one of the theories that the group has been working on is that you have some sort of a leaky torus, and that has been studied for different galaxies and different objects. And again, go read Pepe and Martin's paper review. So this galaxy shows, again, extended soft X-ray emission. We can see here in the soft band. This extent is more prominent in the cone direction, as we can see, when compared to the model PSF in red, but it also exists in the cross cone direction. Going to higher energies, this is another one of those galaxies in which you can see extended hard X-ray emission. And in this case, we have only hard extended emission detected in the cross cone. And finally, which I think it's one of the most the interesting parts for science that can be done with access, is when you have information about when you have good spatial and spectral resolution, like you can get with Chandra, and you can get information about the spectral properties of that region, the spectral properties in a single pixel, you can do this. So basically, you can extract the spectral information from different regions of the AGN to analyze possible different emission mechanisms in these different regions. So in the case of NGC 5728, we extracted the cross-cone spectrum, and actually we merged these spectra into one, because basically number of counts. And but we also extracted the spectrum of the extended bicone in the nucleus. And something that is really important and interesting about this target, and actually it's for me, which is interesting about this whole thing, is that when you look at this spectrum, what you see, at least most people, is that you end up having some sort of unidentified features in the spectrum of this AGN. So context here, when we extracted this spectrum, we are able to extract the spectrum only from the extended emission. So if you see here, these two pi regions here, they are my spectral extraction regions, and they range from 300 parsecs to about 1.6 kiloparsecs, which is 1.5 arcseconds to 8. So we are not sampling the nuclear emission in these sample, in this spectrum. So merging the spectrum from these two regions, we get this. And again, I'm going to repeat because this is important. This is not coming from the nucleus. This emission is extended emission. And we see this. So these images, these features, they appear as features to the red and to the blue of the iron K alpha line, and they are so far unidentified. They've been reported, similar features reported by Peter Maxing in the recent Chandra study of Markarian 34, in which we call them spectral wings because they appear to be two wings to the iron K alpha line. But in Markarian 34, they were detected, and the Peter's analysis suggests a line of sight velocity of 15,000 kilometers a second. So in Markarian 34, this high velocity gas was detected within the nuclear region, so 200 parsecs. But in NGC 5728, this was detected only in when you're sampling only the extended emission. So this emission that we detected has, regarding of its source, it has the projected velocities that are consistent with UFO velocities. So you have relativistic velocities happening in this narrow-line region here. We don't know what it is, but there is something moving really, really fast in the narrow-line region of this target. And why is this important? Well, first, because this is was so far in it a feature that we didn't know about. And actually, now that we know that it has been identified in other AGN, we can maybe do a more a survey, let's say, of some objects to see if these features are can be found in other objects. But most of that, more than that, these features, they have they carry the ability of solve that very puzzling AGN feedback problem, in the sense that if these features are detecting the narrow-line region of this AGN with relativistic velocities, they could potentially carry a very substantial amount of kinetic power into the ISM, and they can be capable of perturbing and disrupting gas in the bulge of the galaxy, which will facilitate AGN feedback. So we need more statistics, and that's what we are hoping for. We need more statistics to get more information on these features. But one of the things that it's important to take from this talk is, even though we don't know the nature of these features, where they come from, or we have more information about them, these wings, they can be a very important feature in a new feature of the spectra of CT-AGN that may have a very important role in generating efficient AGN galaxy feedback in their nearby universe. So this is something that I think it's one of the things that we should keep an eye on for the future. And again, Access will help us with all the science that can be done in the narrow-line region of this AGN. So thank you.
Great. Thank you, Anna. That was a really good talk, really beautiful images. So if anybody has questions, again, please raise your hand. So I'll ask the first one. So, I mean, when I see these images and I sort of think about, as we, go farther away from us in redshift, there's going to be more obscuration, there's going to be more Compton-thick AGN, and just thinking how these feedback processes might, be more or less important. Do you have any ideas on that? Like, do you think these type of feedback processes will sort of increase in redshift, or how do you think it changes as we go back in cosmic time?
Well, I think the kind of information you can get is different. Let's put it that way. So when you study targets that are nearby, and that like these targets, or like the sample of Seyfert, nearby Seyferts that Access will observe, you can get much more information about what's happening in these regions. So if you go back here to that amazing image of, for instance, the Markarian 573, which was done by Paggi et al., you can see just by looking at the image, as Helen shown, you can see the effects of this AGN host interaction just by looking at the X-ray image. And of course, feedback is important in other times, but I think the kind of detail that we can get, that we're going to be able to get with X's for this kind of science is the most exciting part, at least to me, of this topic, let's say, this subject of the host interaction in nearby AGN, because you can't really resolve details if these objects are very distant. So you have to take that into account, it was one of the things that Helen and I we talked about when deciding on the X sample for this part of the science, which is we need nearby targets, because they are the targets that will give you some information, and you can disentangle different and particular mechanisms happening in the narrow line region.
Great, thanks. So I see we have a question from Chris. Go ahead.
Hi, no, well, firstly, thanks for a really nice talk. It was really interesting. A quick question on the spectral wing. So the higher energy wing, to what extent can that kind of be modeled with an ion-26 line? Can you sort of squeeze 926 line in?
Yeah. So I wish I could have had more time to talk about this, but this was a very hard decision to make, because I wanted to focus more on what science X's will be able to do. But in this case here, the models that we have run for this spectrum, and believe me, I ran so many models to try to fit these wings. What we call the red wing here, this feature cannot be, we were not able to fit it with any kind of models. We tried a mix of photoionization and thermal emission, and we couldn't. But for the blue wing, some of the models, they model it as a blend of iron-25 and iron-26. But it's really hard for us to let's say, judge these results, because we don't have a lot of counts in this band. So it's really hard. And again, for great science should be done with X's. It's really hard to disentangle the what's going on. The models can't do it because you don't have a lot of counts, or you don't have good statistics. So there is the possibility that this is just iron-25, iron-26, which would have very high velocities as well. But we were not able to confirm that information.
Okay, great, thanks. Yeah, I mean, this is really one quick thing to point out is that with Axis, in addition to the great signal to noise we're able to get, many times more photons, we fully expect the spectral resolution to be rather better as well than ACIS.
Exactly, and this being something so new, in the science of AGN host interaction, I think it's an extremely interesting topic for the X's, the science that can be done with X's.
Yeah, and one sort of exciting thing to share from literally just a couple of weeks ago is that some of the prototype testing of the Axis CCDs that was done by Stanford and also MIT has shown great results for the spectral resolution. I think it was something like 130 EV at 6 keV. So now, in laboratory conditions, but 10 years before we fly, so that was 9 years before we fly. So
yeah, that'll be great. And actually, these features, and I'm not going to go there, but this is just a comment. These red features, they have been seen before. They have been observed in the literature. There's no information about what they can be. And actually, in one of Mike's papers, I think, on NGC 4151, in which he has a HETG Chandra spectrum for NGC 4151, you can see a feature to the left of this iron K alpha line, and it's very prominent in the spectrum. And so these features, they've been around for a while, but we just never paid attention to them, or we just didn't have or don't have enough resolution to detect them with a certain level of confidence.
Thanks, great stuff.
Yeah.
Thanks.